ask you that the quiz that we have on Thursday,
Yes.
will it have today's lectures material as
No,
well?
no, so it's only Sean's stuff.
Okay.
Yeah. I'll do one in 3 weeks or whenever
Okay.
at the end of my set.
And the guest lecture as well, right?
That won't be part of the quiz, but they will be part of the...
Exam.
yeah, not Uli. So not the one that's already been, but the other ones will be.
All right. Thank you.
No worries.
Hi everyone. Hi. Can you hear me through the mic? It's coming through the mic? Yep. Yes? Okay, great. Thanks. We'll get started because I want to get away as soon as possible as well. So I just wanted to start off. Hi everyone. I haven't lectured yet, so you met me at the start though. So Steve. I'm going to be talking about imaging. So Sean's done a lot about sensing. So I'm going to talk about imaging. That's my area. But first I wanted to run through the stage 2 information just briefly. Any questions you have, you can kind of raise them now or in your or also in your tube, but I just thought I'd quickly run through it so everyone's across it. So basically, stage 2 is your chance to analyse the problem that you've chosen. So you've already chosen a problem. You've all investigated the various problems. So there was 4 clinical problems we presented. Hopefully some of your group has looked at different papers and analysed them, gathered some information. So now you've got a little bit of information about that. You've chosen a problem, and now you really have to do a deep dive into that problem. So we're thinking about solving the problem, but we haven't actually sort of come up or locked in our solution yet. We're going to analyse the problem to make sure that we are on the right path to solving that problem in the most appropriate manner. So it's so basically you've founded your company, you've got your founders, you've assembled your team, and you've chosen your problem. Now, you need to define and analyse specifically what your problem is. You'll write a report, no longer than 5 pages. Sounds short, but again, those 5 pages need to be dense. You need to be really brutal with what you include and what you don't include, and everything should be precise and concise so that you can fit everything you need to fit into those 5 pages. It's not easy. So where am I up to? Okay, so this is, if you attended the guest lecture by Uli, you'll sort of, this is sort of the first stages that he was talking about, the gate 1 stage, I guess you could call it. So the idea is that you're planning your project out, so you're really identifying all the key factors, you're really honing in and defining your problem so that you can then proceed with the sort of the development. Because if you go down the wrong path, then that's going to cost you a lot of money, a lot of time. So you want to make sure you're sort of heading in the right direction to begin with. So you can think of this as a document to convince major stakeholders, both internally and externally. To convince someone, you don't just need to tell them all the positives, but you need to analyse and justify your position. So it doesn't have to be all good news, but any bad news that's in there you need to sort of identify so that your case is compelling and so that it sounds realistic. Because if you just tell them all the good stuff, they're going to look at, well, hang on, there's all this bad stuff here. There's all these challenges that you haven't identified, so I don't trust that you've adequately analysed the problem to go forwards with it. So potentially this could be like for directors or shareholders to unlock the next stage of funding. Maybe it's for investors to actually unlock their funds, so they'll give you the money to go forward. Or it could just be so that they unlock the next stage so you can proceed with what you want to do with your proposal. Back up all your arguments by evidence. Otherwise, it's just not convincing. You can just make an ambit claim, but no one's going to believe you if you can't back it up. Also, you need to communicate well. If you can't understand what you're saying, then it's not convincing. So you need to be able to understand it. It has to be readable, easy to read. You know, your directors, your shareholders, they're not going to spend time trying to understand what you're doing. They just want to read it, understand it, move on. So consider the whole document and make sure there's a consistent narrative. That's really important to creating a really nice report. I won't go through all these sections in detail, but the information's there. So basically, you need to give background to the problem. The next stage is a market analysis and competitive assessment. So this is where you sort of outline the whole market. You look at the size of the market, you look at the competitors, maybe some kind of hurdles to entry in the market. Look at some of the legal aspects, so IP. Is there some critical IP in the field that you will be rubbing up against potentially, or maybe you'll create some nice IP that you can look at? So what's your freedom to operate is another key phrase, I guess, there. What's the regulatory pathway for you? So what classification is your device going to be? The classification is based typically on your intended use. So you don't need a solution in mind necessarily, although I'm sure you've got some kind of solution in mind, but that'll kind of be more about what your intended use of that device is. So, you know, is your plan to go to the USA? It means you need FDA approval. What class? Are you going to be class 1, class 2, class 2B? Are you going to do a 510K? Are you going to do a PMA? All that stuff. What's going to be needed for that? And then reimbursement strategy as well, potentially. So Medicare, I guess the US equivalent, Medicaid or Obamacare or whatever. How does that look for your device? Critical product requirements. I haven't actually put up the information about how to write a good requirement, but I'll do that probably today or tomorrow. It's just a bit of a guideline on what requirements are. So basically, if you don't know what your product has to do or what's required of your product, then you can't design it. So you need to outline your requirements first, and then you can design to those requirements. You can test if you've met those requirements. So that's critical at this stage. And then some decisions and recommendations. Given the analysis and information you provided previously, what do you recommend? What's your path forward? What are the key challenges? And how might you go some way to mitigate those challenges? 5 pages, so you can put a lot of information in graphs that you can't put in words. You communicate much more effectively in pictures. Pictures are great, but you can't just put a picture there. You need to also refer to it in the text. It should be sort of backing up something that you've claimed in the text. So a sort of a pretty trivial kind of example there. You might have a graph of, size of the market for all different jurisdictions, and your text might refer to that. You don't have to describe the whole figure. Then you don't have to say, look, US is this, UK is this. That's all in the figure. But then you can say, look, the 3 biggest markets are US, UK, and Australia. So then you've got one sentence, and you've got all the information to back that up in a plot. So label and refer to all plots in the text. A picture or a plot just hanging on its own without being referred to in the text is just nothing. And hopefully you've got a company name or a letterhead or something by now. If you don't, you need to make one, make a logo, and chuck that on your report. So this is just some more detailed information on that stuff. And then just the same general expectations of quality of analysis and argument and quality of communication. These are really important. As I said, if you don't have a compelling kind of argument backed up with evidence, no good. If you haven't communicated that well, then it's not understandable. People won't get what you're saying. Then they won't be convinced. Cool. Any questions regarding the next stage? Fantastic. Awesome. This week you're meeting or you've got your allocated time with your expert. So that'll be interesting. You can sort of bounce ideas off them and get a sort of a good start for that. All right, cool. Let's move on then. All right. So imaging. This is our friend the cavefish. I put this up in the first lecture. Can anyone remember how this was imaged? Fluorescence imaging, microscope imaging. So light emitted from the sample due to fluorescence. I'll talk about that not today, but in the next lecture, what fluorescence is. This could be called a functional image, I guess, because it's sort of labelling different parts of tissue based on their function. And it's just a nice image, so I like to put it up. Okay, so what will we learn today? What's an image? Different types of imaging, a bit of a background to what is imaging. Good place to start, I guess. I'll talk about light and electromagnetic radiation and sort of some simple models as to how to think about light. This is sort of pretty fundamental, probably year 12 physics stuff. I won't go into too much depth, but it's just important to kind of define a few things so that when we talk about how light is interacting with matter, how we're detecting it, you kind of have an understanding of the basics there. Then we'll move on to talking about cameras and lenses, how lenses create an image. Again, probably year 12 introduction again. But I guess the purpose of that is to have that understanding so then we can think about how that relates to how we're going to image something. So those sort of fundamentals are important as to how we kind of apply imaging. Depth of field and what influences it. Again, principles of operation of digital camera sensors. So I'll talk about how digital cameras work, how digital camera sensors work and their characteristics, and then sort of how to read specifications, what they mean, and why they're important for imaging. And then I'll finish with how we can choose what type of sensor we want for a specific application. Cool. All right, let's get into it. So first, an image. What is an image? This is the Google definition. So quite a few different kind of things there. Essentially, it's a representation of something. That's the kind of overarching theme there. And the plot on the right shows the use of the word image over time. So image used to mean kind of probably that first one, representation of the external form of a person in art, or kind of a, you have an image of something, or this is my image, this is what I'm presenting to you. And then there's a big uptick there in sort of the 40s, 50s, 60s, and rising up until the 2000s. So what do you think happened around that time? Cameras, computers, digital cameras, all that cool technology. And that, so that kind of made this other definition of what an image is. Before that, people didn't know what cameras were, didn't know what an image was. They called it a photograph. But this sort of digital stuff started happening then, and now we have this idea of an image, which is how we'll think of an image today. I guess by sort of 2000, that kind of concept had matured, and it kind of tapers off there. So the origin is Latin, related to imitate. So essentially, we're imitating something, we're representing something as an image. So I guess a bit of a definition that we can use is it's a visual representation of the spatial distribution of a quantity or attribute. Typically, when we think of an image, you might think of like a photograph. I guess that's a representation of the light intensity that's incident on the camera. But it can be anything, really. It doesn't necessarily need to be that photograph or camera type image. You can create a synthetic image in a computer, and it's a spatial distribution of an attribute. Or you can measure the reflection of ultrasound, which is also just a spatial sampling of any measurable quantity. So essentially it's just sensing, but you're sensing across the whole field, creating and then creating that's kind of that image. So that's what we'll talk about when we talk about imaging. And so what's a digital image? A digital image is just that stored as digital data. So essentially what it is an array of numbers. And those numbers represent a certain quantity or attribute, typically of your sample. Usually we look at these, we visualize a digital image by assigning a brightness to that pixel. But it doesn't necessarily represent brightness, but that's just how we're looking at it. Or it might be a colour. What a digital image does that an analog or like a photo doesn't is that it allows us to have these hard numbers in there, and then we can perform maths on them. So that's really cool. We can get other information out of it than just the spatial representation. We can calculate other attributes out of it, or other data. So many different attributes can be imaged. This is a typical photograph. It's just the light reflecting off. That's Murray. That's my dog. We've got fluorescence. So this is the light fluoresced by the sample when it's hit by a certain wavelength of light. So this is an emission, an example of emission imaging. All the points on that fish are emitting light, and we're looking at that light that's emitted. Whereas the photograph is the light that's reflected. We can have an X-ray image. So this is the light that's transmitted through the sample. That's an example of transmission imaging. So those are all examples of different modes of optical imaging, looking at electromagnetic radiation or light. But you can also look at other things like ultrasound, that's sound, pressure waves. So ultrasound is formed by reflecting pressure waves off an object and reading that back. And there's other types of images like this one, which would be like a radar image. So again, that's representing a certain sample attribute. It's not what you typically think of as like a photograph. And you can even create an image through other means such as this. So this is an image of height or topology, and that's measured by atomic force microscopy. Does anyone know how atomic force microscopy works? You get a little needle, and you basically go as close as you can to the sample, and when it gets really close, it repels that, and you can measure that, so you know how high you are. Then you move across a little bit, and then you do another one, and you know how high that is. You go across the whole thing, and then you get an image of the surface of your sample. And you can represent that as an image on the left, where the height is represented as a colour on a colour map, or the right is like a 3D render of an image. So what's so good about imaging? Well, basically it's sensing, but better. So why is it good? Well, it gives you regional quantitative information of properties for computer analysis. So essentially, think about, I think Sean probably talked about blood pressure. So put a cuff on, you can measure your blood pressure. It's like a blood pressure for your whole body. What if you could image the heart and show the blood pressure everywhere inside the heart and at the surface of the heart? That would be so much better. It's hard to do. It also gives you qualitative information, I guess, so you can present this regional information as an image, you can then read it and a human can intuit something from it. So this is another, it's not just a line or it's not just a number, you can actually see because it's got that regional information. Mostly it's non-contact and non-invasive, so you don't necessarily have to touch your sample to image it. Usually you don't touch the sample, which has all sorts of advantages practically, and also you're not disturbing your sample as you're doing it, and you get pretty pictures, which is fun. So why don't we just do it all the time? Well, there's some things that are hard about it. Often the temporal resolution is quite low. It's like taking 1 million samples, or millions of samples even. So where a sort of typical sensing application, you take one sample, you can take it really quickly. This you have to take millions of samples, so that can be a bit slower sometimes to generate a whole image. Sometimes you get a lot of data, it's a bit hard to interpret. A line, a number going up is easier to interpret than maybe some kind of image. But that's where computers come in, and also, they can maybe be less sensitive and accurate and less quantitative than a sort of a purpose-built sensor. And also typically, though not always, it's sort of larger equipment, so you can't put an imager inside the heart very easily. But you can maybe put a little sensor in there. So what are some common forms of imaging? A lot of the forms are based on the electromagnetic spectrum. And I'll talk about what that is in a minute, but basically it's light at all of its frequencies. So we have X-ray, transmission imaging, so how much light is transmitted through a sample. That can be a bright field microscope or an X-ray. We have some emission technologies, which is that fluorescence, where the sample actually emits light and we detect that light. And that can be gamma rays from like a PET scan. We can do some fancy things because light is a wave, so we can get what's called phase contrast, where you get interference fringes due to the wave-like nature of light, and also dark field because light scatters. So we can measure that kind of attribute. And there's also resonance, which is a radio frequency kind of detection based on resonance of your atoms. And that's MRI. You would have heard about MRI. And there's other types of imaging as well. We can use acoustic properties, which is ultrasound. Put a little pulse of ultrasound in there. It bounces back. That's a reflection. And so we're measuring the pressure wave as opposed to an electromagnetic wave. And then there's atomic force microscopy, which I spoke about before. It's just a bit of a background. Imaging is all those things. We won't talk about all of them in detail, but we'll talk about X-ray in detail and some of the microscope technologies in detail. And if we have time, we might talk about some of the other medical imaging stuff. But we'll see how we go for time. All right, so let's learn a little bit about light. This is a nice picture generated by the US Air Force, I believe, trying to get people to sign up because you can do cool experiments and wear cool glasses. You'd never wear those glasses in doing a laser experiment. We've got proper laser goggles. But that's light, so we'll learn about light. So is it a wave or a particle? You probably heard of this debate or this kind of concept that light is a wave or light is a particle. Doesn't really matter. We're going to use both of those models. We're going to think of it as a wave and as a particle, depending on what we want to learn or how we want to sort of, what application we're talking about. So we use both those models to help us understand how light interacts with matter. And that'll help us understand how to utilise light in different situations. So hopefully you all are aware of what the electromagnetic spectrum is. Essentially, this is the spectrum of light. Now, light can occur at lots of different frequencies. So we'll be thinking now as like a wave, I guess, and we have, or a particle. So essentially, light can exist at different frequencies. We have visible light, what you would normally think about as light, and that exists in that sort of space of 400 nanometers to 700 nanometers. That's the wavelength of the wave of light that is in the visible spectrum. Gamma rays are also part of the electromagnetic spectrum with a very, very short wavelength. And radio waves are also the same thing as light, just with a very long wavelength, up to sort of 1 kilometres long. And across the entire spectrum, that whole spectrum is used for imaging. Okay, so just a bit of history. Maxwell was sort of the first to consider light as an electromagnetic wave. That's him there in the sort of 1800s. And he generated the first colour photograph because he realised that light of different colours is just light of different wavelengths. And so he could filter out the different wavelengths and then put them back together to get a colour photograph of that bow. So if we think about light as a wave, what are some of the properties of a wave? So think of it as a sinusoidal wave. A wave has a wavelength. We can call that the colour. So in visible light, the wavelength is directly related to the colour. It's also got an amplitude, and that's like the intensity or the brightness of the light. And it's also got a speed. Speed of light. The speed of light can change in different mediums. So the sort of speed of light limit that you've all heard of is the speed of light in a vacuum. But in other mediums, it can travel faster or slower. So we have this equation then that relates frequency to speed and wavelength. The take home from this is that frequency is inversely proportional to wavelength. So we have a wave, we can talk about it as a frequency as well, and it's inversely proportional. So if you have a long wavelength, then you have a low frequency. So frequency is also colour, essentially, and usually we talk about frequency and sort of wavelength sort of interchangeably in terms of light as a wave. So then in the 1900s, Max Planck came along. He won a Nobel Prize in 1918 for his quantum theory. Very famous physicist. He's even got his face on the Deutsche Mark, so he must be a pretty big deal. And he said, hang on, no, light is energy. And it's just a little packet of energy. And that's how he's going to think about light. Like a particle of energy. So he said it's just a discrete quanta, it's just a particle of energy. And that energy is proportional to the frequency. So when you say it's a wave and it's got a frequency, I say, no, it's a particle and it's got an energy. And there's a constant to convert from the frequency to the energy. So if something has a high frequency, it's a high energy photon. Call them photons. So you can think of it as a little particle. And if it's got a high frequency, it's got a high energy. So high frequency is that gamma ray X-ray side. So that is high energy. So we can talk about high energy photons, that's sort of X-rays, gamma rays, that kind of radiation. Low energy photons are at the other end. And you can relate the frequency and the energy through Planck's constant. So that's just a bit of background, and I'm going to talk about some of these concepts sort of as we go through. But just have those sort of ideas in your mind that light is a wave with a wavelength and a frequency, and that frequency is proportional to its energy. Okay. So this will give us a bit of a framework for talking about light and how light interacts with matter, how we can detect it, and how we can use it. Okay, so that's just a bit of background, I guess. So we'll talk about cameras and imaging now. So this is a photo from 1900 of what at the time was the world's largest camera, taking the world's largest photograph. It was a bit of a PR stunt. You can see the size of that camera. It's pretty good. It's a photographic plate. So the camera was 400 kilos. It needed 15 people to operate it. And the plate that it used, the photographic plate, was 8 foot by 4.5 feet. That was huge. And it took a really nice big photo of a train. So this camera, 1900, is essentially the same. It has the same components as all cameras today. It's got a lens, it's got an aperture, and it's got some sort of detector. And it's the same basic components as what's in your eye. Your eye is just like a camera. You've got a pupil, which is like an aperture. You've got a lens, which focuses the light onto your retina, which is like the sensor or the photographic plate. And this is more like a digital camera because you've got an optic nerve which reads the retina, reads the information on the retina, and converts it into a signal that is then read by your brain, which would be like a computer. So cameras, been around for a while. This is sort of just a brief history. These are film cameras. So this is how it used to be. Hands up if you've used a film camera before. Okay. Cool. So I'm a bit older than you guys. I've taught this subject since 2012. Every year the sort of hands that go up are less and less because these just aren't around anymore. So these are mostly Kodak cameras. Kodak, has everyone heard of Kodak? Yeah, so huge company in photography, and essentially they didn't change much all over those years. Got more sophisticated, but nothing really different. And that's a film there. If you have never seen a film before, it comes in like a little cartridge. It's a long roll. It's got some gears. You kind of go along, take a photo. It's all held in a dark casing, and then you can put it in a machine. It will develop it chemically to change the light-sensitive compounds in the film. They'll turn from dark to light depending on how much light was on them, and you'll get what's called a negative, which is like a transparent film. I'm sure you all know how cameras work, or should know. These are some disposable cameras there in the middle too. These were great fun. I remember going on holidays as a kid. We'd each get one of these cameras. You go out, take photos. You didn't get to see them for months, so you didn't know if they were any good or not. You'd end up throwing half of them away. Not like today, but essentially the same thing. A lens, an aperture, and a sensor. So this is how a camera works. We've got an object, we've got a lens, and we've got an aperture. Creates an image on the light sensor, and that senses the light, so the lens focuses the light onto that light sensor, and then we read that out somehow. And that way we get a representation of the object. So first we'll talk about the lens and image formation, and hopefully this is all just a refresher from year 12 or whenever for you, but we'll just go through it. So there's some definitions. Thin lens approximation. This is a sort of a simplified lens idea, and there's some rules that go with a thin lens approximation which allow us to think about how images are formed by a lens. There's the focal length. So the focal length is the distance to the focal point. It's that little f. The focal point is the big F. This isn't the focal plane. This isn't where things are focused. It's where the light bends and always passes through. So that's not where the image is. And there's another definition of lens power, which is the ability of the lens to bend light. How powerful is it to focus light? And the optical power is 1 on f. So essentially 1 on the focal distance. So if you have a very short focal distance, you have a very powerful lens. Just makes sense there. So a couple of just rules about that relate to the thin lens approximation. So for a diverging lens, light that comes in, it diverges. So any light which is parallel to the optical axis, which is that line down the middle, sort of going horizontally here, any light that is parallel to that axis will diverge away on a path that, if you followed that path back, it would land on the virtual focal point on the other side. And the inverse of that is that any light coming in, which is converging onto the focal point on the other side, will be diverted and diverged to be parallel. I know, have I missed something? I have. Okay, so okay, I've missed a slide here. That's okay. So a converging lens is just the opposite of that. So if you have lines parallel, light coming in parallel to the optical axis, then it will be converged onto the focal point. So that's the first rule of a converging lens, and I'll add that slide in later. The second rule of these thin lenses is that any light passing through the centre will just keep going, doesn't get diverted. And that means that's from travelling in any direction. So the other rule is for light travelling parallel. So if you think about a light ray coming in sort of through the centre parallel, that'll keep going straight through and pass through the focal point on the other side as well. So how does this relate to image formation? Well, we have an object, we have our lens, we have our image plane, and there's our focal point. So let's take a few points of rays of light coming off this object and see where they go. We'll do some ray tracing. So we've got one from the top of the head coming straight across. Where's that going to go? Straight down through the focal point, exactly, thank you. Down through the focal point. And that's going to end up there. If you can see what I'm doing, just here on this sort of point on the image plane. Now, what if I take a line from the top of the head and draw it straight through the centre of the lens? Same point there. And you can draw all the other lines, they'll all converge from the top of the head, they'll all converge on that point. And so at that plane, that image plane, all you get is light, at that point on the image plane, all you get is light coming from the top of the head, so it's focused on that image plane. So the light from the top of the head is imaged onto that image plane, that point on the image plane. Likewise with the feet, a light ray coming parallel to the optical axis, passing through the lens, passes straight through the focal point again, and lands on the image plane at a certain spot. Light going through the centre will do that, and so you get all that light from the foot focused on that point here. And you can do that everywhere and you get this image. So at this image plane, for this focal distance, this object distance, we get an image of that object. What do you notice about that image on the image plane? It's upside down, it's flipped, inverted, exactly. You probably know that's how your eye works as well. The image on the back of your eye is inverted too, but our brain just flips it back. Same as cameras. What else do you notice about it? Smaller, teeny tiny, little, demagnified. We can change the size as well with a lens, and typically the size will change because if I want to put a sensor here and I want to take a photo of you, I'll need a pretty big sensor if it wasn't made smaller. And likewise, if you want to take a photo of something really, really small, you want that image to be bigger, you want it to be magnified. We can do both those things. Okay, so magnification. Magnification is determined by the object distance and the image distance. And remember, that image was formed because of this focal point, and so that's all determined by the focal point. So the rule is 1 on S1 plus 1 on S2 equals 1 on F. If you need this, it will be given to you. But it's important to note that the object distance and the focal point will change the magnification. So we can also express it like this, whereby the ratio of the object distance and the image distance gives you the magnification, or the focal distance and the object distance gives you the magnification. Note that there is a negative there, that's the inversion happening. So that's not making it smaller, that's inverting it, making it upside down. Smaller would be a number less than 1, that's demagnification. So magnification of 1 is just your object and your image are at the same point, at the same distance from the lens, and they're the same size in that case. So magnification of 1. So just a bit of sort of more depth there. The constant focal length, as an object gets closer to the focal point, we get this thing happening. We'll get more magnification. I'll bring the whole thing up. So if I push my object closer to the lens, I get more magnification to the same focal point, focal distance. And also the image is pushed further away. So this is important when you're thinking about how you're going to make a camera, how you're going to make a lens. What focal distance do you need? Are you taking a picture of something far away that you want demagnified? Are you taking a picture of something up close? If you want lots of magnification, you need to be very close to the lens. And then you need a long back distance. If you want to take a photo of something far away and demagnify it a lot, then you're usually up. The sensor is up close to the lens and your object is far away. So this is sort of all talking in an ideal world, but lenses aren't perfect. You can't manufacture them perfectly. So there's these things called aberrations. The sort of typical aberration that we might get is a spherical aberration. A spherical lens is really easy to make. And when I say a spherical lens, I don't mean it's a sphere, but the surface is part of a sphere. So it's got the same kind of arc everywhere. And it's not a great shape for a lens. It's easy to make, and typically kind of traditionally it's easy to make if you're making it by hand, grinding and polishing a sort of a piece of glass. But what you get is that every point on the lens doesn't converge onto the same focal point. And so in that case you get some aberrations. You don't get a perfect image. Nowadays we can make things more, we've got much more sophisticated manufacturing techniques, and we make aspheric lenses which don't have this problem as much. But similar things can happen if you don't have a perfect lens with every point on the lens focusing on the same point, on the focal point. And you can get something like this happening, where the image is kind of skewed in that kind of circular manner. Some other lens aberrations. Chromatic aberration. So I didn't talk much about refraction, but refraction is actually frequency dependent, so colour dependent. So all colours will refract differently for the same change in medium. Refraction is when light bends. You should hopefully know what that is. So essentially, you get what's happening there. Blue light will focus on a different point to the green light, which will focus on a different point to the red light. And so you'll get an image like this where the colours are all separated and not lining up. It's called a chromatic aberration. Nowadays we can kind of have colour-corrected lenses. We can have compound lenses as well, which I'll talk about a bit later. And some of these things aren't as prevalent, but you do need to design around them, I guess, and be aware of them. So that's lenses. I'm just going to sort of give you a quick rundown of everything in there, and then we will talk more about the applications of it. So then we have aperture. Most cameras have an aperture, or there's an implied aperture from the size of the lens. Aperture is just a hole. It's like your pupil. Camera, if you've ever done photography, has an aperture that's typically adjustable. So the aperture basically controls how much light gets in. If you have a really teeny tiny aperture, you're blocking a lot of the light that's coming in. And also what it does, more importantly, is control the depth of field. And the depth of field is the depth of the image that's in focus. So you can see that middle line of that paper. This is a photo taken of some text, which is at an angle. So the top of the page is further away, the bottom of the page is closer, and the middle of the page is somewhere in the middle. And the lens is focused on the middle of the page there, where it says depth of field, and you can see that there's a finite depth to what is in focus. So if you have a narrow depth of field, then only a little bit is in focus. Only that middle line would be in focus. A long depth of field or a large depth of field, you'd have basically all the text would be in focus. And depth of field is mainly dependent on the aperture, and it's also dependent or related to the magnification and the focal length. Typically a large aperture, or always a large aperture, you'll get a small depth of field. So you have a really, really big lens with a really, really big aperture, you get a very, very thin depth of field. This is why photographers can take really good images. They have a really large lens, which gives you a lot of light, so you get a really nice image, and have a small depth of field, so you get the effect, which I'll show you, where you have your foreground in focus and the background out of focus. And that's sort of a nice photographic image. If you have a small aperture, you can get a large depth of field. So why is this? Well, have a look at this ray tracing. So we have a large aperture. Essentially we have no aperture, so the aperture is just defined by the size of the lens. If we have a little dot here that we want to image, we can do some ray tracing of that dot, and all those lines will converge onto that point. If I have a dot that's further, and I'll get a nice sort of, nice sharp image of that red dot there. If I have one that's off that plane, further away, this is what you'll get. Basically, it's not in focus. You've got light coming all the way up here and ending up here on the image plane. You've got light coming straight through, ending up there on the image plane. You've got light from this sort of part of the lens passing through there. And so you get this blurry image. It's larger, it's blurrier. So that's a thin depth of field. But if I put an aperture in the way, well, that's a thin depth of field there. If I put an aperture in the way, I can block out some of that light that's not converging on the right spot. And I only get this light coming through, and I get a nice sharp image of the red dot again. But now with the blue dot, I've got one passing through the middle, and I get this here. So I don't have this ray coming up here and landing here and making a blurry image. All I get is this one here, landing pretty much on the right spot on the focal point. On the image plane. And the same again, and then I get a sharper point there. And so in this case I have a thick depth of field. All that in that grey there is in focus, essentially. It's because of the small aperture. And this is just an infographic that I pulled off the internet, talking about f-stop. So f-stop is a photographic terminology for the aperture, when you have an adjustable aperture. And you can see there a large aperture, we get a thin depth of field. Up here. So only the cat would be in focus. And the rest is blurry, as denoted here. And then as I stop down my aperture, make it much smaller, then the whole thing, the rabbit, the tree, everything's in focus. So that looks something like this. Large aperture, we have that flower, sharp focus, and the background is all blurry. It's kind of a nice image. On the other side, maybe not so nice. One isn't better than the other, it just depends on what your application is. So that's how aperture affects depth of field. And focal length and depth of field. This is how focal length affects depth of field. You can think of this as like, say I want to take a picture of a mountain. It's really far away. So I'm going to want to have a short focal distance. I'm going to have my object far away. I'm going to have my image up close. And if you take a photo of a landscape, all of that is in focus. You've got kilometres and kilometres in focus. And that's that top line there. So you've got a large, the lines that you're drawing, the rays are coming in at small angles, you get a larger depth of field. If I have a microscope and I'm taking an image of something up really close, and I have a really powerful lens, my film's plane, my sensor is further back, my object's really close, I have these sort of larger angles, I have a thinner depth of field. So typically if you have high magnification, you'll have a thin depth of field. So some of these things, as I said, are mitigated. You're talking about a single lens there, but actually cameras these days have heaps of lenses. So the one on the left is a schematic of like an SLR camera. It's got, I think, 8 elements there. These correct things like chromatic aberrations. It allows you to do zooming, where you can change your focal point, change the length, the focal length. The one on the right there is actually a smartphone camera. You can see, I think that's got 16 lenses in it. So pretty sophisticated, and that allows them to sort of have this really good camera, high sort of effective aperture in a really thin kind of space. All right, so perfect time. So that's what I'm going to talk about with cameras. And so those concepts, kind of the fundamentals of that, but we'll talk about how that kind of relates to microscopy and imaging, and so as long as you understand those sorts of things, you can then understand how we can apply it to microscopy. So I'm going to give a bit of a demo now, or try to. So this is to do with compound lenses and focal distance, etc. So I bought this from Kmart. It's a smartphone attachment to turn your smartphone into a microscope. It costs about $2. Essentially, if you can't see it, essentially it's just got a lens here, and if you look, there's a light as well. That's it, and you attach it to the camera. So I'm going to try it with my computer. Got my photo booth. Why is this not working, camera? Oh, this should be videoing, sorry. I don't know why this isn't on video mode. There we go, that one. Right. That one. Does anyone know how to make this work? It was working before. Let's just close it and try and open it again. Why aren't you working? Slight problemo. I might have to get this going some other time because it was working before and now it's not working. If I do that. If I do that and press this, will it take a video? It should be working. I'll try and get this working as we have a break. So I think we'll have a break then. I'll try and get it working. So after the break, we'll talk about the more meat of the light sensor, which is probably going to be a bit more interesting to you. All right, thanks. So maybe we'll have 5 minutes. Any questions, come and ask. Any help with this would be appreciated. Yeah, that's what I was just thinking.
Maybe if you unplug it.
Yeah, that's what I was just thinking, but I'm not sure. Do about it.
Yeah, you might have to do some like document camera of your screen thing.
Yeah. All right. All right, thanks everyone. Thanks. Let's get started. So I got it working. The old restart worked. Okay. Hi. So you can see me up there now. The light's not great, but maybe I'll try and change the light a little bit. Better? A little bit better, not really. Full lighting. There we go. Is that cool? So, I'm here. Yeah, you can see me. I'm in focus. So, if I stand here, I'm still in focus. What's going on with the depth of field? Thick depth of field. Okay, why might that be? Got a teeny tiny aperture, got a teeny tiny camera, and I've got a long working distance, so I've got demagnification. So I've got a large depth of field. Okay. All right. So what's going to happen when I put this on? I'll become blurry. Why? Yeah, kind of. Yep. I'll have higher power lens. I'm going to increase the power. I'm going to decrease my focal distance. Increase the magnification. Can anyone tell me why there's a light on here? Think about what light is going into that camera right now. It's all this light reflecting off everything. It's everything. What happens if I add heaps and heaps of magnification? I'm just going to have light from a tiny little area. So everything's going to get really dark if I don't have more light. So you have to add more light. So we're going to try it. It's not going to look great because it's super dusty and horrible. So this is like a compound lens. You can change the properties of your system by adding another lens in. Just got to get it in just the right spot. All right. So, hi. I'm super blurry. All right. I've got hardly, and it's like looking down a tunnel, but I've got hardly any depth of field. But can you see what's in focus? Something really close. It's the back of the thing. So that's really close in focus. Now, if I take something, if you want to look at something, if I hold something up really close, get it in just the right spot, it's in focus and it's really super zoomed in. And I can see all that dust and whatever that crud is on there. Project. So, heaps of magnification. So I've just changed the whole system. I've increased the magnification, so my object has to get up really close. Maybe my shirt's kind of cool too. There we go. Yeah, so it's pretty cool. It's like $2 from the from Kmart. It's a lot of fun. Yeah, so I have to get, I have to add more light. I have to get up really close, and that gives me my magnification. All right. I can gross you out and do my arm. I was looking at like scabs with my wife. It was really gross. And moles, if you're going to mole, but yeah, so yeah, it's pretty cool. And if you look at your finger, I was going to do my finger, so you can see it's dirty, sorry, but you can see all the ridges, that kind of thing. So I've increased the power, increased the magnification. I have to move closer, so that S2 distance S1 distance is closer. The focal distance is smaller, so increase the magnification. And I've made a microscope, and this is how microscopes work. You have to get really close. You put your lens right up against the thing, because you've got to bend all that light around. You've got to have really high power. Anything else to say about it? That's probably it. Depth of focus is really thin as well. So I can't actually get close enough to lose it, unless I maybe put something inside there, but you can see like I get there, you can see it, and if I get closer, maybe I can't get close enough to, but anyway, it's only like this big. Whereas before you could see me from all the way back there. So it says now. Really different. So that's a compound lens. All right. Cool. Worked. Great. Now, how do I get out of this? Question, close. All right. So that's lenses. So we can create an image on our image plane. Now, how do we detect it? Because that's the really important thing, so we can turn it into a digital image and do some cool stuff to it. We'll go back to the lecture. All right, so detector. So digital images. All right. I define a digital image as essentially an array of numbers. This is the first digital image ever produced. So it was produced on a computer. It was like a scanner. Each pixel was manually read in 1957 on a really super old sort of computer. But that's quite a while ago. Digital cameras didn't come around till a lot later. And I think this was essentially so they could digitize documents. It was a pretty low resolution image. I think it was sort of, 100 pixels by 60 pixels or something. But anyway, that's the first digital image. So the first digital camera was 1975, Kodak. So Kodak, famous for going under because they didn't move with the times, they actually invented the digital camera. It weighed about 8 pounds. It was pretty low resolution, 0.01 megapixel, not many pixels, black and white. Took 23 seconds to take an image. So not super awesome, but still pretty cool for the first one in 1975. You can see the major components. Still got a lens. There's some detector in that blue box. And there's also some electronics to read out the signal. And then we have something there on the side. Does everyone know what that is? Cassette tape. Still know what that is. And essentially it's just a magnetic tape, so you can store magnetic information, such as ones and zeros, digital information. I used to have, when I was very young, a video game console that took tapes. It's just like a disc. It's the same thing. Then we have sort of moving along a bit in the 90s and stuff like that, when technology got a bit more advanced. We had cameras that looked the same as the other film cameras, except they had a digital sensor in them. Best thing about digital cameras is you can see your image straight away and you can delete it if it looks no good. Or retake it as well, obviously. You can see sort of there's an SD or a flash card there. So a digital storage medium to hold your pictures. And then, today, so that they don't exist anymore since essentially iPhones or smartphone manufacturers created these small cameras. You don't get those digital cameras anymore. You can get professional SLR cameras, such as one on the right there. It looks the same as the film one I showed you before, but it's got a digital sensor in it. And again, camera phones, every phone has a camera, and they're actually getting, pretty super awesome at taking photos. So again, that's a camera chip. A digital image is a representative of the image in terms of discrete intensity values or just numbers, just quantities. We call them pixels, and it's stored in electronic memory, digitally. So a camera chip is just an array of millions and millions of tiny little light sensors. It's just sensing light. And in 2009, the CCD, which is the sort of one of the main and one of the first technologies used in camera sensors, they won the Nobel Prize. So that gives you an idea of the kind of impact that digital imaging has had. So they didn't invent the digital chip, but they invented the CCD process, which went into digital cameras. So important specs. What do you think, if we have this chip where we're sensing our image, we've got our lenses, we've made an image, what are the important things that we want in our sensor? What are the important things to note when we're trying to sort of design a system or use a sensor in our camera? Resolution. Yes. Sorry? Dimension, yeah, the size, yep. Pixel size, they're related. What else? Noise? Sensitivity? Sorry? Say again, sorry? Color reproduction, yep. So reproducibility, linearity, speed as well. These are all things we want to think about, and we'll talk about all that stuff soon. So we have scientific cameras as well. They look like this. So usually for science, we want something low noise. We want sort of high speed potentially. We want them to be pretty sensitive. We want to do different experiments with them because they're pretty expensive. So we can have like attachments to attach different lenses on them. And the one on the right there has a specific camera interface. So it's not just USB, although now often they do use Ethernet. But maybe we want to take a whole lot of images really quickly, and we don't want to put a big disk on there. We want to put them straight to the computer. We might need a special image capture or a data capture card in our computer and a specific interface, which you're not going to do if you just want to consume a product. But if you want to do scientific work, you might need that. And they're boxy, they're ugly. So that's scientific cameras. But essentially, they're just the same as any other camera. So sensor arrays, there are two types, CMOS and CCD. And they're essentially the same. They have a similar way to detect the light, and the way they differ is how they read out that signal. So if you look at the process at the bottom there, essentially it's a photodiode array. This is true for CCD and CMOS. The photodiode array is the pixels, and it converts the photons that come in, or that are incident on that pixel, into an electrical signal through what's called the photoelectric effect, which I'll talk about in a second. Then there's some electronics and some structures there to read out that signal from the pixels. So that's an analog signal. It's charge, essentially. It's electrons. And we need to somehow read that from the pixels. And then reset the pixels and then take another image. So that's how they differ. That's how CCD and CMOS differ, and I'll talk about the details of that in a minute. Then that signal is fed to analog to digital converters, ADCs. So we can get a digital signal from that analog signal. The ADC controls the bit depth, which I'll talk about as well. It's another important quantity or characteristic of a camera chip or a camera. And then that digital information gets sent to a digital storage, usually your computer, something like that. Okay, so how does it actually detect the light? What happens? So again, just a sort of superficial physics explanation, it's the photoelectric effect. What happens? We have photons. Remember photons? I spoke about them before. Particles of light, and they have energy. Now, if they have enough energy, then we have this, if they have enough energy, they can free electrons from a material, and that material in the diode. So they come in with an energy which is greater than the work energy. That's what that symbol denotes. And the work energy is the energy needed to liberate those electrons. So if we have a photon come in, it's got enough energy, it's got the right colour, or enough energy, it's got enough colour, it can liberate an electron. And that electron is our signal. So the sensor array consists of many pixels. Each of them is a photodiode working on the photoelectric effect. The work function is the minimum energy required to liberate that electron. So you have to have the photons have enough energy to liberate that electron. So that is just essentially a repeat of Planck's equation. You have a threshold frequency, the work required is energy, and so you have Planck's constant in there. So to convert from the threshold frequency, the light frequency, to the light energy that is required to liberate the electron. So that's how they work, essentially. Now, how you read that signal is different for CMOS and CCD, and I'll talk about that in a minute. So essentially, these are the important specifications. Sensitivity, how sensitive is it to light? And that's defined as quantum efficiency, and that is the percentage of photons hitting a surface that produces an electron. Sometimes a photon might hit the surface, it doesn't actually produce an electron. And the percentage of the photons that actually are incident on the surface that produce an electron is quantum efficiency. And that's dependent on the incident frequency, the incident energy of the light, the colour of the light. So there'll be a peak efficiency at a certain colour. Maybe it's green light, 532 nanometers wavelength. That might be the peak efficiency. That's where the most electrons at that level will liberate an electron in the surface. And that's how we measure sensitivity and define sensitivity in a camera chip. Frame rate. If I want to take pictures of something moving or something like that, then I want to be able to take lots of images quickly. Otherwise I'll miss it. So frame rate is typically frames per second, but it's not really a fair comparison, because if you have a lot of pixels to read out, then it's going to probably be a bit slower. So pixels per second is probably a fairer kind of metric, but frames per second is what's typically used, because that's what you sort of see. But it is pixels per second. That's sort of the gate of or the technology has a pixels per second rate. So you can do things like take a smaller image, take a region of interest, and only read out those pixels, and you can get a faster frame rate for the same chip. Noise. So how sure am I of the number of electrons that have, number of photons that have hit the chip? There's noise in that signal. The intensity isn't, the intensity readout isn't perfect, so you have some noise, and that's typically measured in electrons. So it's kind of, it's a pretty sensitive measurement, and we measure noise in terms of electrons. How many electrons are there, plus or minus, for a certain intensity level of light? Pixel size, dimensions, native and effective. I'll talk about that more when we talk about microscopes, but essentially what's the size of each pixel? That's the native pixel size. It's the size of the pixel on the chip. So if I have my chip and I get out a tiny little ruler and I measure the pixels, that's the native pixel size. Resolution, how many pixels? I'll put that in quotations or whatever, because usually the resolution of a chip is talked about in terms of megapixels, how many pixels there are, but resolution actually means something else, which I'll talk about next week. But that is an important specification. As you'll probably know, all the camera, you buy a new phone, it says it's 10 megapixel, 15 megapixel, whatever. That's how many pixels there are. It means how sort of fine an image can you take. How many measurements can you take across your whole field of view. And then there's dynamic range. Dynamic range is how many different colours or grayscales can you measure or store. So the digital information, the digital image is stored as integer values. It's not a continuous, so the intensity is not a continuous measurement. It's stored as integers, and that's determined by the analog to digital converter. So you might have a 16-bit camera, and that means you can represent intensities 65,536 different intensities within your image. So each pixel can have a number between 0 and 6,535. And that's the total number of intensities that you can assign to one pixel. Often an image is 16-bit as stored, but the camera is only 12-bit. And so they sort of scale it up, or they just have empty bits, because 16-bit is a typical TIFF sort of format. Or cameras are 8-bit. Most cameras are 16-bit these days, or 12-bit. If you have colour, each colour is represented separately. And usually it's an 8-bit RGB, something like that. So you have red, green and blue, each represented as an 8-bit number. Gives you 24 bits in total, gives you 16 million colours in combination. So that's important if you think about dynamic range. There's often in your camera phone, you might have a setting that's called high dynamic range. So that's when you want to measure something, an image where there's some really, really bright bits and there's some dark bits as well. So if you have someone, standing up here with a spotlight on them, they're going to be really bright. But you want to be able to measure all the light, or represent all the light in between them and also the dark spaces as well, potentially. And so you need a lot of dynamic range. You need to be able to store a lot of different grey levels, from dark to light. So a typical kind of spec sheet will look something like this. We've got technical data on the left, and these are some of the sort of typical numbers there. Resolution, again, that's in pixels, so that's the number of pixels. And it gives it as a sort of width by height, sorry. Then you have pixel size, which is measured in microns usually. So that's each little pixel on the chip. That's the native pixel size, 6.5 micron by 6.5 micron. Peak quantum efficiency, as I said, it's frequency dependent or wavelength dependent. So 590 nanometers typically is the peak, and it's something like above 60% quantum efficiency for this camera. If you look on the right, you can see the spectrum of quantum efficiency for wavelength of light. So green is 532 in the middle there, and then that's the peak sort of in the middle. 590 is sort of red, so that's the peak efficiency of the detector, and then it tapers off if you go outside of that. So most of the light that you're seeing is going to be like the red light or the green light or the visible light in there, which is good because that's what we want, the visible light, when we're using a camera usually. Dynamic range, again 16-bit, it's called bit depth. Readout noise. Now the readout noise is going to be dependent on the frame rate. You can speed it up, but you'll get more noise for this camera. And there we go, we have median electron noise of 1 electron. That's pretty good. Imaging frequency or frame rate, again, full frame fast scan 100, full frame slow scan 33. So they're adjusting the settings there to get more or less noise depending on what scanning rate you need. So that'll be adjusting the readout protocol to either get more noise or less noise. Exposure time range. Exposure time is pretty important. You want to be able to take a very short exposure if you're taking an image of something really fast. If you're taking an image of something really dim, you probably want a long exposure because you've got to gather more light. You've got to let it expose for longer. And a selectable region of interest will allow you to get different frame rates for your region. And then the optical input, as I said, this is a scientific camera, so we want to have some kind of interface to attach different lenses to for different applications. And then again, data interface. So scientific camera, this uses camera link, which is a kind of a fast streaming, a sort of a high-speed bus for the for the image capture, or uses USB 3 as well. Okay. So that's some specs and characteristics of cameras, but how do they actually work in terms of CCDs and CMOSs? How do they read out? Yeah, good. So CCD is read out thus. We have our pixels. We have our photoelectric material here. So that's silicon. When light is incident on this, it liberates some electrons, so it creates a charge. So there's a charge there after exposure to light. And that charges electrons. If we put a positive voltage on this electrode, all those electrons will gather here. And so that's during exposure. Then what do we want to do? We want to read them out. We want to know how many electrons are here because that's proportional to how much light was incident on that pixel, on that section. And what we can do is read them out by shunting them across a pixel. This will start up soon. So then they all go to here. Let me do it again. I'm going to do it again over to here. So this happens like as a production line until you get to the edge of the chip, and then at the edge of the chip you've got some ADCs there to read out the signal. So basically you have to read out each pixel one at a time. So that's pretty slow for a CCD. But what's cool about a CCD is that it's very low noise. So you don't lose many electrons as you go across here, if you use this process. And then you read it out to an ADC pretty much straight away. So the electrons don't go very far from this kind of this pixel to be read out. So very, very low noise. Also large fill factor, what's called fill factor. Fill factor means how much of the pixel is actually utilised as a sensitive element. So large fill factor, most of this pixel is actually sensitive to light and generate electrons to be read out. That means that it's more efficient because you've got more area to convert light into signal. It's pretty expensive to make these things, so they're pretty expensive, they're pretty slow, the readout is slow, but they're very, very low noise. And they're quite sensitive as well because of the large fill factor. So these are sort of CCDs that are typically used for a scientific camera. If you want those characteristics of, you don't really care how fast it is, but you want something really low noise and something sensitive. I'll just play that again. So this is how the pixel is read out. Essentially, you're just shunting the electron signal across pixels. One at a time, you read it out into an ADC. Okay. So that's CCDs. What about CMOS? CMOS is what's termed an active pixel. So if you look at the image here, each pixel has the photodiode, but it also has some electronics on it. So it's got its own transistors, it's got its own amplifiers. This means that it can read the signal out, or the analog signal out anyway, much more quickly because the pixel's actually doing most of the work. But the trade-off is that you get this kind of fill factor issue where not all of this pixel is actually part of the sensitive element, only this part of it is. So for this example, it's sort of like a quarter of the pixel. So you're wasting light. There's going to be a light incident on these parts which aren't going to be contributing to your signal. So that's sort of a lower efficiency. So the charge gets read out by these transistors and these electronics, and then basically you just read it out through a copper wire, a copper track, and then it goes to the ADC and gets converted to a digital signal. So if you know anything about electronics, you'll know that that's going to amplify the noise. It's going to give you some noise because you've got to read this analog signal out through a sort of a typical sort of a copper track, just a simple copper track, which is going to add noise before you convert it into a digital signal. So they're pretty cheap to manufacture. This is what's in most consumer cameras now, and even some high-end cameras. In your phone, it'll be a CMOS chip. They're much higher frame rates, which is what we want, particularly for consumers, and they're sort of quite a bit cheaper to manufacture than CCD chips. And to take care of some of the fill factor issue, so this issue that the whole element isn't actually a sensitive element, the whole pixel isn't sensitive to light, what they do now is put a little lens on the top. So that lens doesn't need to be sort of super high quality or super good, but what it can do is focus any light which is on this whole area onto that photodiode. So that gives you a larger fill factor. And it takes care of a lot of that low efficiency. So the CMOS sensors today are actually getting much closer to a CCD type efficiency. A lot of newer cameras are CMOS cameras now rather than CCDs, even scientific cameras. Okay, so a bit of comparison. CCD, slow readout, slow imaging rate, maybe 15 frames per second if you're lucky. Video, video is 24 or something like that, so it's not even video rates. But they're very low noise, less than 1 electron RMS in the case of a certain type, an electron magnified CCD. Sorry, electron multiplied CCD. So less than 1 electron noise. You can't ask for better than that since an electron is your signal. And they're pretty high efficiency, 70 to 90% quantum efficiency. So 70 to 90% of the photons that are incident on that detector will create an electron. So CMOSs are much faster. You can sort of get to 5,000 hertz for 2 megapixel, even higher nowadays. High-speed cameras, slow-mo cameras are CMOS. But they can be pretty noisy, 5 electrons RMS, something like that. And often less efficient, sort of 50%, so that's quite a hit on efficiency, which is, fine if you're taking a picture of, or a video of, the football or something where you've got lots of sun and light and everything. But if you want to use it for a microscope, it's not great. But the efficiency is getting better, actually, with these micro lenses. And we have these new cameras they call scientific CMOS, which are somewhere in between. They've just made a really nice CMOS type detector, so they can get the noise down to 2 electrons, which is sort of similar to CCD. Quantum efficiency is up to 70. Again, sort of low-end CCD territory there, and relatively fast readout, 200 hertz. That's quite a bit faster than 15 frames per second, 15 hertz, but nowhere near as fast as a CMOS detector. But anyway, so that's sort of a scientific CMOS that has been produced specifically for scientific purposes. They're reasonably expensive. Cool. All right. So how are we going to apply this? Let's talk about a couple of applications and whether we'd use a CMOS detector or a CCD detector. Okay, so I've got two applications there, fluorescence imaging, microscope imaging, and dynamic imaging of a very fast moving object, but a large object. All right, so have a think about what might be used for what. Let's talk about this one first. So this is a fluorescence microscope image of a skin cell. I'll probably talk about this much more in detail when we talk about microscopes and resolution. But essentially it's an emission technology, so you hit that sample with a certain wavelength of light and it'll emit some light of a different wavelength. You can filter out the sort of excitation light and you just get the light that's emitted. So it's a cell, it's really tiny, tiny, tiny. There's not a lot of light coming off it. So it's pretty dim, it's low light. We're looking at low light conditions. It's fixed. It's not moving. It's on a slide. It's been prepared. And so it's a fixed sample. So it's not moving at all. And we're talking about very high magnification. It's a skin cell. So that's, microns order. So it's pretty high magnification. Again, that's going to contribute to what? Low light. So you've got not much light coming off it because it's dim, and also it's really small, so you don't have much light coming off it. So who wants to guess or work out what type of chip we'll use for this? CCD or CMOS? Anyone? CCD. Yes. So we want an efficient sensor because we have low light. We don't want to be waiting there for 4 days to take an image. We don't have many photons coming off this thing, so we need something that's pretty efficient. We don't care about exposure time. It can be pretty long. It's not dynamic. We don't have to have a sort of a flash photography of it. We don't care about frame rate because it's a fixed sample. So we're not trying to capture a moving object. And again, high magnification, low intensity. We want low noise, efficient, sensitive camera. So CCD. So CCDs are often used in microscopes. Okay, dynamic imaging. We have a moving sample, moving very fast. We have low magnification. So it's actually demagnification. So we're taking a picture of something really big, we're taking all that light and we're putting it onto a tiny little chip. So we've got a lot of light coming in. It's sort of a bright environment. It's not a low light environment. We've got a moving sample, so we want short exposure time. What happens if we have a very long exposure time? It takes a long time to take in all the light to generate our image. What happens? What happens? If I have a long exposure time and I'm taking a picture of something that's moving, it might have moved from the time I start taking the image to the time I finish taking the image. So what do I get then? I get motion blur. So I don't want that, because then I can't see what's happening. Also, I want high frame rate because maybe I want to capture the motion of it. Maybe I want to see how it's moving. And also, maybe I just want to be able to capture it at all. If I miss it, I want to be able to take a picture quickly afterwards so I can actually see the part that I want. So I need a high frame rate as well. Low magnification means more light. So I don't care about sensitivity so much. What I need is a short exposure time. I need a high frame rate. And so what would that be? What chip would I use? CMOS chip, exactly, because that's the other one. CMOS. So CMOS is high speed, but less sensitive and more noisy. So this application would be perfect for a CMOS. All right. That's it for today. So what have we learned? We've learned a definition of an image, knowledge of different types of imaging. I just touched on that briefly. We've learned some important properties of light to help us think about how light interacts with matter and how it's used for imaging. And that'll become more important tomorrow as well. Or sorry, in 2 weeks' time when we talk about X-rays and when we talk about also resolution and fluorescence. Properties of camera lenses, how they create an image, depth of field, what influences it, and principle of operation of digital cameras, those two types of cameras, characteristic specifications, and how to choose a camera. All right. Any questions on what I presented today? Fantastic. So, next week we'll talk about resolution. We spoke about resolution a little bit in terms of how many pixels there are, but that's not real resolution. Resolution is the spatial resolution. What's the smallest thing you can image? So we'll talk about that, how we measure it, what determines it for an optical imaging system, and how we can improve it. And then we'll talk about high magnification imaging in terms of microscopes and some applications. So, thanks. No, so it's just the previous 3 weeks, just Sean's lectures, and there'll be another one.
How about include that guy's lecture?
I don't think so. Maybe after, but I don't think it's that lecture.
Alright, but it's up to last week, right?
Yeah, and then I'll do a quiz after my 3 weeks. So I'll do 2 more lectures, and then there'll be a quiz based on that material.
Alright, got it. Thank you.